do you mean by modelling, and how is modelling relevant to TIMS?
It is a modelling system. It makes models of block diagrams. That's how I look at it. And every communications textbook is full of block diagrams.
Okay.
And each one of those blocks is usually a simple element. And that's what these modules are, simple elements of communication systems.
How is modelling related to a real system? Is it equivalent to the real thing? Because it's not a simulation, it's obviously
not
a
simulation, it's pretty equivalent to the real thing. The only concession is it's scaled down in frequency.
TIMS is known for its unique block diagram approach. Why did you choose to have individual modules which correspond to individual blocks in the block diagram rather than, say, having a whole experiment in one to save time?
You lose all the flexibility, you lose all the degrees of freedom when there's a module that does many things at once.
Okay. And is that flexibility a positive for students?
Absolutely. As this has developed, some modules have become a bit more complex, but mostly they're very elementary and they do one job and one job only. Only a certain number of fundamental building blocks in a communication system and rearrange them in so many different ways. It says somewhere in one of the manuals that you can do at least 50 experiments. Well, that's being very modest. You can do, I'd like to say thousands of experiments, that's probably not true, but hundreds anyway, with slight variations, which had it been all fixed in a box, none of those variations would have been available.
And what were the main priorities?
I didn't want circuit analysis design or any involvement in that at all. There had to be little boxes that did the job without the student knowing why. They learnt why in another course.
Different
We didn't
issues.
want to be soldering resistors and making things. We wanted boxes that worked, which were compatible. Full stop.
Okay, so you just wanted them to operate at a systems level, like a telecommunications block level?
I suppose you could. Well, block level, straight out of a textbook.
Okay, in accordance, and what, to concentrate on the theory of telecommunication fundamentals?
Yeah, forget about the electronics.
Okay.
As I said before, they learnt that in a different course. I wanted it to be very basic, very fundamental. No unknowns, but every signal had to be set to its right frequency or amplitude by the student. No calibration knobs. You can't set things up by numbers. You have to know why each frequency is what it is. You have to know why the amplitude is set to what it is.
Okay, and is that the reasoning behind why the knobs haven't got any calibration markings?
Absolutely. It's setting the right levels, not knobs.
Okay.
And if you get it wrong, you see what happens. You can get everything wrong. You can have the wrong frequency, wrong amplitude, wrong this, wrong that. It'll still operate, but if it doesn't work the way you want it, that's your fault, and you've got to find out why. You've always got access to every signal in your system, and one of them is always the best one for synchronizing the oscilloscope too. You can always set things up the correct way, and that, if you get it right the first time, that's not really a good idea, because you think, well, this works, I'll go home now.
Yeah, I didn't learn anything.
No, but the best thing to do, if you do set it up the first way, is then to say to yourself, what would happen if I change this frequency 10 times? What would happen here, there, or the output, or whatever? And so misalign it. This is where you pick up all sorts of things you hadn't at first realised. But those experiments are written up step by step, supposed to cover every possibility. They obviously don't, but I tried to. And then at the end, a few curly questions, hopefully curly questions. Whereas the lab sheets, can I talk about the lab sheets?
Yeah.
They were really meant to show you how to set it up in a hurry without any theory. That's up to you. It's just how to set it up and one or two pitfalls to avoid. But
like a quick start.
A quick start.
Quick start, let's get going.
Yeah.
And I believe that I've got from existing users is that that's very helpful for professors who already have their existing curriculum and they just want to know how to fit TIMS straight into their curriculum by quickly building up the experiment, by getting the procedure up and running quick smart. The yellow is analog? and the red is digital.
That's absolutely right. If they're on the left, they're an input to the module, and if they're on the right, they're an output from the module.
Okay, so if we look at this module here, it's pretty obvious what's going on. We've got a sequence generator, which is a repeatable source of digital data. It has both an analog and a digital clock. It has a synchronizing output as digital. It has 2 digital channels out and 2 analog equivalent channels out for doing analog work, such as
analog channel. Another important feature is you can connect anything to anything, any output to any output, inputs to inputs. You can misconnect, make mistakes, and you can't damage anything.
The system's been designed to be
robust. The other big feature is that all the modules are plugged together and they're mismatched intentionally so that when you pull a lead out from an output, the output amplitude doesn't change. So most modules are designed to give an output at some standard reference level, which we call a TIMS analog. Oh, we're talking analog at the moment.
Yep.
TIMS analog reference level. So if the module has the capability of increasing or decreasing its output level, it's best to set it to this level, that is the reference level, which is 2 volts peak. And that keeps the signal noise ratio of the signals you're interested in. We say 40 dB signal noise ratio or better.
Okay.
And that's a good working reference level. I think I first put it in so that I, the instructor, could send signals to every bay. So that if they were building a receiver, I could send them all sorts of signals, which they didn't have to build. So all the systems are connected by the trunks cable.
Which is like an analog sort
which is an analog cable, which has a bandwidth of a megahertz or so. And they all went back to what we call the master bay.
Which was your one?
Which was my one.
Okay, hidden away somewhere with the answers.
Hidden away. And then I could send all sorts of signals to each bay, and they didn't have to be involved with the generation of the transmitter, modelling of the transmitter. Then, alternatively, or they could talk to each other via their bays.
Okay, using the in-out.
Using the in-out.
Sort of daisy chain.
Yeah.
So like in comes from the neighbour and out goes to the neighbour. And what's that good for? Students interacting with each other, or
whatever you can dream up. I can think of thousands of things.
Okay.
Or you can even set up your own transmitter on one system and then move to the next bay and do some receiving tests.
Okay, it's just a bit like distributed analog processing in a sense. Yeah.
I also used to put join bays together by unknown processing systems, like a filter or something, and they had to measure from one bay to the other and work out what was in the middle, and work out what sort of signal would go through it. So they had to communicate from bay to bay through an unknown channel. But that used to give me such a thrill to hear them say it, and you heard them say it every first experience with meeting TIMS. They said, just like a textbook. In fact, better probably.